Okay, so I'm going to talk about abstractions and what they look like in Rust compared to other languages and what the performance looks like. So just a little bit of background on abstractions so that we're on the same kind of page. Abstractions are really kind of what we deal with as programmers. They're higher level concepts, and it's a way that we go and ignore essentially the irrelevant parts of the problem and focus on the detail that's important. Abstractions are very helpful because they allow us to clearly express what we're doing and also reduce the cognitive load and errors that we get when we're coding. So, I mean, there's numerous examples, we're all familiar with it, but some of them are, for instance, just using a higher level language like Java or C Sharp instead of like C or assembly. Other things are using classes or interfaces or traits, using iterators and functions instead of imperative loops. There's tons of these. Now, considering they're so important in programming languages, it's quite interesting because abstractions are not always free. So today we're actually going to look at iterators as an example of this. So let's look at some C# stuff here. At a very high level, we could have some algorithm like start, like you've got a bunch of numbers in two vectors, and if the first number, at least if the number in the first vector is larger than 2, then we want to multiply, the first vector and the second vector together, or the elements at least, and then add them to a sum. So that's a sort of expression in, pseudocode. You can then write that in C sharp as, take vector A, zip it with vector B, pick out pairs where, the first one's larger than 2, multiply them together and sum them. So this is a nice sort of high level abstraction. And then in theory, the low level is that you'd get some assembly that looks like this. In reality, though, that's not the assembly you get. So we'll have a look at this in a second. So here is what C sharp looks like. So if we go and take the iterator approach here, so now VA and VB are both vectors. They've got 20,000 elements in them. If we take the iterator approach here, the nice one, then we land up with us taking 400 microseconds. If we go and do the direct loop, where we just iterate through, just with a for loop and just take indexes and, do the usual thing, that is nearly 10 times faster just because of the way that C Sharp deals with iterators. Then you can go lower. So you can go and manually unroll that loop in C Sharp, and you can put unsafe around it to get rid of bounce checks and all that sort of thing. And you can make it another 4 times faster than the direct loop. And then if you want to go completely crazy, you go and write this AVX code here, which we're not going to go into in detail for the C# stuff. This is in GitHub, so you can check it out later if you want. But that takes this 47 milliseconds and brings it down to, microseconds, and brings it down to 2 microseconds. And this is pretty much as fast as you're going to get on, well, my processor. So if you plot the whole thing on a graph, it's pretty telling. I mean, the AVX version is down here. The the iterated version's up here, and the direct loops here. So for something like this, yeah, you definitely want to use this instead of this because this is actually extremely expensive. So yeah, that's C sharp. Let's look at Java next. Java doesn't really get away with this either. The doesn't really have a zip function in Java, so I wrote my own one, or I pulled in the Google Guava library. The Google one comes out at 900 microseconds. Sorry, my phone's realized I'm saying Google. Shut up, phone. The hand-coded one is 265 microseconds, and the direct loop is pretty much as you'd expect in C# and Java, they're both about 45 microseconds. So yeah, I've just added those to the plot there. And again, you're better off just doing, straight up indices again, because yeah, it's just how it works. I'm assuming Scala fares better, but I haven't actually tested it because they do make more use of these sort of iterators and stuff. But I'm still expecting them to be relatively expensive. So yeah, if somebody's done that, let me know. So yeah, now that we've done that, let's look at Rust. So the first thing I should note, I've changed the axis here, zoomed it in. This used to go up to 800 at the top here, and it's zoomed into about 50 here. So this is where the direct stuff is in C# and Java, and this is where all the Rust results are. So why is this? We'll talk about that next, but Rust abstractions are often even faster than a straight up loop. And the times we're looking at here are 3 microseconds up to maybe 6 microseconds. And I did a direct AVX2 implementation that came out at 1.9. So these are all very close. And we'll look at the AVX stuff, and you can decide later if you would want to go down that path. But essentially, the reason is that the compiler knows all the tricks. So it knows how to do branchless programming. It knows how to use AVX instructions. It knows how to unroll loops, inline functions, that sort of thing. So the net result of this is that you can decide to do something using an iterator. You can use either of these sort of patterns or anything else you really want to do. And they're pretty much going to give you very fast results. So it allows you to kind of express the way you like to do things. I personally kind of like this way of doing things. It's very easy to understand, and you don't run into issues where you're going to run off the end of the array or anything strange like that. So yeah, next we'll talk a little bit about what SIMD instructions look like, and actually look at some of the support that we have in Rust for them. So as a quick refresher of what SIMD is, single instruction, multiple data, it's essentially modern processors have very wide registers that you can use so that you can actually do operations on multiple data elements at the same time. So if you've got, you do one instruction and you operate on like 4 or 8 items. So if we look at SSE2, this is the older one. The registers you'll see in a debugger are called XMM registers. They're 128 bits wide. These are available on all Intel and AMD processors. If you have a 64-bit one and you're doing 64-bit code, it's pretty standard. You're pretty safe using this for everything. And it allows you to get 4 32-bit ints or floats into a single register. Then AVX is the newer one. By newer, I mean anything post-2013, so it's still pretty old. These are 256-bit wide registers. You've got AVX and AVX2. The AVX standard is mostly floating point, and AVX2 is mostly integer stuff. And this allows you to get 8 32-bit integers or floats into a register. So once you've got that register loaded, you could add it to another register. You could multiply it, shift it, do an AND operation. There's like probably thousands of instructions there. And it's really, really fast because you're typically issuing a single instruction and the process is going to operate on 8 data elements at the same time. So it's pretty quick. AVX, just a couple of caveats. It may not be faster on older Intel CPUs. They have some issues with clocking. They also don't like doing unaligned loads and things like that. But on more modern hardware, that really isn't a problem. And if you do feel like you want to use AVX instructions, it's a little easier to use than SSE because they're non-destructive. They don't overwrite themselves, the registers. So, but yeah, you'll see that when you get into it if you're kind of interested in that. So in Rust, this is kind of the interesting stuff. It's an area that's rapidly evolving. You can just ignore the code on the right for the time being, and we'll talk about what's available on Rust at the moment. So there's currently stuff on stable Rust, there's stuff on unstable Rust, there's some future stuff that's happening, and we'll talk about whether you should use it. So currently on stable Rust, you don't actually need to do these sort of AVX instructions directly most of the time, because if you're happy with the 3 or 4 microseconds for that loop, and you don't want to get down to 2, um, LLVM will automatically vectorize loops and use these sort of instructions anyway, provided you tell it what processor you're using. So if you target the correct processor by changing your cargo config in your project or Rust flags, you set target CPU to native, it'll use whatever's on your machine. If you set target CPU to a specific one, like Skylake, that does support AVX2, it will also generate those instructions. There's some good documentation in standard Arch. The documentation in standard Arch will tell you how to detect processes and do those sort of things. If you do want to get lower level, currently on stable, the only way to really do it is to use intrinsics, and only x86-64 Intel is supported. And they are luckily the same intrinsics as in C++, so there's good documentation and stuff. This is very unsafe and it is very low level. And you've got to go read the Intel Intrinsics Guide, and there's various other references as well to understand what's going on. You've got some crates like SIMDs for slightly higher level code if you want it. But yeah, that's pretty much what you've got. And then you can produce code that looks like this, which, yeah, it is faster, but it's a lot less maintainable. Currently on unstable Rust, you've also got intrinsics for ARM, WebAssembly. WebAssembly is going to have intrinsics as well, and various other things. So that's going to be pretty cool when they start stabilizing some of this stuff. You've also got inline assembly for most platforms, including ones that don't have intrinsics. And then you've got some cool crates like Faster and Packed SIMD for higher level code. And that stuff really simplifies this kind of thing, but it's not available on stable yet because this is a very active area and changes are expected. So they're not going to stabilize stuff until they're really certain that they have got the right approach. So in order to do that, they've formed a Rust portable SIMD working group, and they're working on the kind of standards that might go into a standard SIMD kind of thing. And that will allow for you to have like a generic set of instructions and vectors that work across different processors like ARM and Intel and those sort of things. Because there's a lot of stuff which is similar, but every instruction's different, and then the way things are packed and aligned is different. So it's a hugely complex problem, and it's going to take a little bit of time for them to solve, but I think we're going to get there at least at some point. So the question is, yeah, should you use this stuff? The answer is maybe. So if we looked at the algorithm that we had before and we compare it to this thing that we've got here on the right, the very simple iterator approach was only about twice as slow as this. So the relative benefit of doing this sort of stuff here is a lot lower than the relative benefit of doing this sort of stuff in a language like C#. If you do it in C#, it's literally 20 times faster. If you do it in Rust, it's only 2 times faster. So perhaps it isn't worth it. However, if you have got something which is extremely performance critical, and it's really going to make a big difference to your life, it's going to make a massive difference to your product or something, maybe it's worthwhile actually getting into this and doing this sort of stuff. A lot of this says, it's unsafe because the compiler can't verify, what these instructions do. They could, if you don't have the correct processor, like if you've got a really old processor and you issue this instruction, it will crash. Likewise, this thing where we're loading stuff from a pointer into a register, this is a load U instruction, so it's load unaligned. If you change this to a load, that will crash. But it won't crash every time. It'll only crash when the pointer happens to not be aligned with a 256-bit alignment. So sometimes it will work and sometimes it won't. And when it doesn't, you'll just get a seg fault. So a lot of these instructions aren't really fundamentally unsafe, but they do things that Rust would consider unsafe. So there's casting, and you've got to understand what sort of variables you have, and you've got to understand the kind of conversions that are going to happen internally. So these are all things that Rust can't verify. So they all, at the moment, go into a big unsafe block. One thing I'd like to highlight here, this is a very useful thing. Chunks exact is really, really useful. So if you've got two slices and you want to take, 8 items at a time, chunks exact is really cool because it'll give you 8 items. And then, you can let it do the loop accounting there. And then we can just do stuff like load those 8 items into a vector and do the operations we want there. So yeah, that'll give you the 8 bits that are there, and then you just need to do something with the remainder. So in that case, we just call into another function that adds up the last 3 or whatever. So yeah, that's kind of like SIMD and Rust. Rapidly evolving, quite interesting. If you want to learn some x86 assembly stuff, it's not a bad place to go and fiddle. So yeah, some conclusions briefly, because we don't have too much time. Abstractions are very expensive in some languages. So for all developers, I think it's really important to know how to identify opcode paths, because a lot of people get told that these abstractions are expensive, and then they'll go back into their favorite language and start replacing every single iterator with a loop. And that's really the wrong approach, because you don't need to do that. You've got to identify where the hot code paths are. So if you're doing very little work inside the loop and you're doing it lots and lots of times, then the loop itself becomes important. If you're doing something expensive inside the loop and you're going through it 10 times, then it doesn't matter. Then just use the iterators. So that's one thing I really want to stress. Figure out and know how to identify where the hot code paths are. So yeah, use classic loops for those and use abstractions elsewhere. Know how to do micro benchmarking and profiling. That's another really important thing. People don't necessarily understand where the hot code paths are because they don't understand how to use tools to identify where they are. You can only do so much by inspection. Then if it's a really hot loop, you could consider doing some more aggressive optimization. So it could be SIMD, or if you're in C# or Java, you can actually use some of the classic optimization techniques like loop unrolling. The JIT compiler is in a hell of a hurry, and it won't actually do those for you. As things improve, the JIT compiler is starting to do slightly more stuff, but it's got nothing on like Rust or C++. It's just in too much of a hurry. You've seen how long C++ and Rust and so on take to compile. There's a reason for that. The compiler is doing a lot of work to make stuff fast. So in Rust, yeah, the equations are a little bit different. Use the abstraction, they're fast. And sometimes it's even faster than using a direct loop because the compiler is able to see what variables aren't being changed and what are mutable and those sort of things. And it's able to do some optimizations, which often result in the loop being extremely fast. The other thing is target the right CPU. Rust won't use those instructions unless you tell it it can. So, if you're building your software for AWS or something like that, you can just go and use AVX because all their Xeons are modern. Let the compiler do all of the hard work. And yeah, if you want to check your assembly, you can add -- emit ASM on your cargo config or your Rust flags. Check out godbolt.org. Want to give this a little bit of a plug. This is a tool which decompiles C++ and shows you assembly, and you can go and check it out for different processes and so on. But the thing is, they also support Rust, so that's really cool. So if you want to go and just copy and paste some code in there and see what it compiles to in assembly and go and tweak it a bit in there, absolutely an awesome tool for that. Then for benchmarking Rust, Criterion is an excellent crate that allows you to do some really cool stuff. So I'd recommend that as well. Then this is a plug here on why people should learn some Rust, because this is originally a presentation I did at work. And yeah, the reasons for that, simply a language that empowers everyone to build reliable and efficient software. And I think the way it deals with iterator abstractions are a demonstration of that. It's also Stack Overflow's most loved language. Yay, hope it wins again this year. There's quite a lot of a learning curve, but it's really useful outside of Rust too. Functional devs will enjoy the type system. There's really good tooling, and there's a cool mascot. And yeah, if you guys want to go and play around with the code or have a look at what I've done, there's the GitHub repo. So yeah, thanks.